Welcome back, AP Chemistry students, to Unit 9. Today we will be talking about Unit 9.3 Redox reactions. Redox is an abbreviation for reduction and oxidation, which is when an atom gains or loses electrons and therefore changes its charge or oxidation state. Now, we've talked about charges of elements before. In Unit 1, we talked about how elements will gain or lose electrons to be like a noble gas. So fluorine will gain one electron to become like neon, to have a lower energy state. And we said for all halides, they all gain one electron. The chalcogens, we said, would gain 2 electrons. So sulfur picks up 2 electrons, and therefore we said sulfur had a -2 charge. Nitrogen and phosphorus, we said, were 3 electrons away, so they'll pick up 3 electrons. On the other side, when we talked about metals, metals have more electrons than a noble gas, so they lose that valence shell to become cations. So lithium will lose 1 electron to be like helium. Magnesium would lose 2 electrons to be like neon. Transition metals have lots of different oxidation states, lots of different charges because of the presence of that D sublevel. However, there were 3 transition metals that you had to know the charge of, those being silver, zinc, and aluminum. And this is what you learned in first year chemistry or at the beginning of the year. And it's a generality. It's true for some of them, but it's not always true, right? So the polyatomic anion sulfate is an ion. The oxidation states here, those charges, have to equal a -2. However, if both oxygen and sulfur are -2, how does that work? Is it just the average of their oxidation states, or is there something more at play? That is the question we're going to answer today. So atoms do have various oxidation states. What you learned in first year chemistry or at the beginning of the year were an overview. And generally speaking, at least for those beginning units or the beginning of your career, you could fall back on them, but it is time to grow up. It's time to get to true oxidation numbers. Determining the oxidation number of an atom within a compound follows a set of rules. First off, any elemental compound, something with a single capital letter, like chlorine gas or nitrogen, phosphorus, or sulfur, we are going to say the oxidation state of the atoms involved are all 0, because they have to cancel one another out, since overall that molecule is neutral. So anything elemental has an oxidation state of 0. In exercise 12, we're asked the oxidation state of the atoms in various molecules. So for this first one, each chlorine atom, we are going to say, has an oxidation state of 0 because chlorine is elemental. Some elements have constant oxidation states. Like when I told you silver, zinc, and aluminum are always +1, +2, and +3, that is because aluminum is always +3, zinc is always +2, and silver is always +1. Other elements that are always are fluorine. Fluorine has only one oxidation state. Fluorine will, in a compound, always be fluoride. Group 1 and 2 metals are also always +1 and +2 respectively. However, everyone else can fluctuate, and therefore those rules that you learned aren't so much rules as they are generalities. Like you were taught that hydrogen is always +1 because it's a group 1 metal. And it's true, hydrogen can lose 1 electron and become just a naked proton, but it can also gain an electron to form an atom with similar electron configuration to helium. So the elements that are always the same are fluorine. Fluorine is always -1. And for the vast majority of the time, we are going to say that oxygen is oxide. There is an exception here, and if you are going for a 5, you can learn that exception. But for right now, oxygen we're going to say is always -2. Fluorine is always -1. So on exercise 12, the compound carbon dioxide is neutral, meaning overall the charges, the oxidation states, have to equal 0. If oxygen is always, or usually, -2, 2 oxygens means oxygen is contributing a -4. So in order to determine what carbon is, what -4 is 0, basically add 4 to both sides, and you get that carbon has to be a +4. So in the compound carbon dioxide, carbon has a +4 oxidation state, and each oxygen has a -2 oxidation state. In the compound water, oxygen's a -2, water is neutral, so each hydrogen has to contribute a +1. So hydrogen in this case is a +1. Now, in both of those examples, the compound was neutral. What if a compound is not neutral? So for the example sulfate, sulfate is a polyatomic anion. It has a -2 charge. When dealing with anions, the sum of the oxidation states has to equal the charge of the ion. So we've been setting them equal to 0. In sulfate, we need to set it equal to -2. So each oxygen is a -2, 4 of them is a -8. So in order to figure out what sulfur is, so we figure out that sulfur is a +6. These rules aren't all inclusive, there are more to them, but if you just remember these few, you can determine the oxidation state of practically every atom in a compound. Again, we are going to say oxygen is -2 for the vast majority, and then everything else should fall into place. In our final example, why don't you pause the video and see if you can determine the oxidation state of sulfur and fluoride. Again, in this case, sulfur is a +6, as just a coincidence. Sulfur can be +6, it can be +4, it can be -2. It just depends on what compound it's in. With that being said, on page 13 in your packet, you are asked to determine the oxidation state of each atom, of specific atoms within a compound. So for the first one, you're determining carbon, and so on. Please pause the video and complete page 13 in your packet. Now, if something is giving up electrons, something has to accept them. So oxidation and reduction reactions are abbreviated redox because they often happen together. A redox reaction is when something gives up electrons and something gains it. Something is reduced when it gains electrons. So if something becomes more negative, we say it is reduced. Something is oxidized when it loses electrons. It becomes more positive. So you can remember it as Leo goes Ger. Loss of electrons is oxidation. Gain of electrons is reduction. Personally, I remember oil rig. Oxidation is a loss. Reduction is a gain. You just need to remember that we're talking about electrons. So in order to determine what is oxidized and what is reduced, you assign everyone their oxidation state and split the reaction into 2 halves, an oxidation and a reduction half. So for the reaction between aluminum and iodine, aluminum goes from elemental aluminum to aluminum in a compound. Aluminum is one of the always. Aluminum is always +3. Iodide, therefore, must be a -1 because 3 of them cancel out the aluminum. Now, it didn't start that way. Elemental iodine would have an oxidation state of nothing. So our two half reactions here is that solid aluminum becomes two aluminum cations, while solid iodine crystals become iodide ions. And while this one is fairly straightforward, they can get more complicated. When you need to figure out what's oxidized and reduced, you're going to add electrons to these reactions. Now, you could just look at them and be like, well, in order for aluminum to go from 0 to +3, it has to give up electrons. Or you can think of it that the charges have to balance. A charge of 0 cannot become a charge of +6. 2 times 3 is 6. To balance the charges, I need to bring this down by adding electrons. 6 electrons would cancel out those charges, and now there's a conservation of charge. Or again, you can think of it just iodine becomes iodide by gaining an electron. Each iodine would have to gain an electron, so 6 electrons had to have been gained by the iodine crystals, or you could balance the charges. In either case, when dealing with a redox reaction, I strongly suggest you get in the habit of writing how many electrons are transferred. So in this case, 6 electrons were transferred. That will become important in later parts of this unit, but it's a good habit to think, okay, I need to know for later how many electrons were transferred. In this reaction, 6 electrons are transferred from the aluminum to the iodine. When those 6 electrons are transferred, aluminum loses electrons. A loss of electrons is oxidation, and iodine gains the electrons. A gain of electrons is reduction. So we would say that aluminum is oxidized and iodine is reduced. If a question were to ask you what is an oxidizing or reducing agent, agents, personally, I remember them as double agents. So an oxidizing agent is a thing that is reduced. So when iodine gains 6 electrons, it's reduced, it's going to force something else to oxidize. So iodine would be an oxidizing agent. Again, I think of them as double agents, so anytime I see agent, I think the opposite. So in this case, the reducing agent would be the thing that was oxidized. Since aluminum loses electrons, it is my reducing agent. Now, the reason we keep track of those electrons transferred is because we can use them to do work. And we've taught you up to this point that in order for a reaction to occur, the two reactants have to collide in the correct orientation and with enough energy. And that is still true, but with redox reactions, what's actually happening is a transfer of electrons. So as long as those electrons can transfer from one substance to another, the reaction will occur. So if we were to separate our reactants, our reduction half from our oxidation half, as long as electrons could go from one side to the other, the reaction would occur. And this is the setup for a battery. In your Duracell battery, commonly called a copper top, this is the net ionic equation that occurs. Zinc reacts with copper cations to produce zinc cations and copper solid. In order to understand this reaction, we need to show it as its two half reactions. So where zinc becomes zinc cations is one reaction, and where copper ions become solid copper is another. In order for zinc to become zinc ions, it would have to give up electrons, and therefore it is being oxidized. In order for copper ions to form solid copper, they'd have to pick up electrons, and therefore it is being reduced. Now, these two would happen in the same container, but if we separated them, we could actually capture that transfer of electrons and have those electrons do work, which is how a battery or galvanic cell works. The two half reactions are separated. So on one side, we have the reduction of copper. On the other, we have the oxidation of zinc. Each one contains a solid component. So we produce electrodes of those solid components. So here's solid zinc, here's solid copper. When connected by a wire, those electrons are able to leave the zinc and travel to the copper. So the zinc is giving off electrons which are negative, so we call this an anode. This electrode is called an anode because it is negative. The copper is gaining those copper ions, so it is positive. We call it a cathode. This is why your copper top batteries are called copper tops. They used to have a top made out of copper and a bottom made out of zinc. And if you look at the battery, the copper end is positive, the negative end is zinc to correspond to the cathode and anode demonstrated in this picture. Because oxidation always occurs at the anode. You can remember that the vowels go together. That's how I remember it. So the anode is going to give up electrons to the cathode, where reduction occurs. The consonants go together, reduction and cathode. As the zinc gives up electrons, it forms zinc cations. And so the anode will begin to decay. If you put this in solution, if you ran this reaction, you would see that the zinc electrode will lose mass. As that copper cathode gains electrons, copper in solution becomes solid copper, and the mass of the cathode grows. Because the electrons always flow from the anode to the cathode. So you can remember it as fat cat. From anode to cathode. Electrons flow from the anode to the cathode. As zinc is oxidized, you produce more and more zinc ions in solution. This solution becomes more positive. As copper is reduced, you lose copper cations. This solution becomes more negative. And so there's a gradual buildup of charge in each half cell. So to prevent this to becoming unsustainable, we add a salt bridge. A salt bridge is a device that contains a solution of soluble salts, so that as the cathode becomes more negative, it doesn't repel electrons. A cation can flow in and neutralize that charge. The anode becomes more and more positive, which would become attractive to those electrons, so an anion is present to neutralize that charge. If a battery does not contain a salt bridge of some sort, the battery will not function. So in the example you are shown here, we have a reaction which contains two solid states. The copper ions become solid copper. The zinc dissolves into zinc ions. Those are both solids, and so we can make electrodes out of them. But you can form batteries out of just ions, like a lithium ion battery that powers your cell phone is made out of simply ions. So that requires us to sometimes use an inert electrode. So for example, iron 2 can oxidize to iron 3. When it does, It loses electrons, but there's no solid state. So for this reaction to occur, we would need some inert electrode. For inert electrodes, you can use platinum, but since this is a public high school, I'm never going to give you platinum. I'll just have you grab some pencil lead, because graphite will conduct electricity and allow the reaction to occur. If you're ever asked to build a voltaic cell, which is another way of saying galvanic cell, try to use solutions that are as close to 1 molar as possible, because we call this standard conditions. A battery is usually made out of 1 molar solutions of your ions. So we would make 1 molar ferric and 1 molar ferrous solution and mix them together on one side. On the other side, we would have 1 molar cupric solution. We can abbreviate voltaic cells using line notation, where we have the reaction in the anode separated from the reaction in the cathode. So for the reaction here, in our anode, we have iron 2 that becomes iron 3. We separate them with a slash to say this is 1/2 cell. The salt bridge we would symbolize with double lines. And then in the other half cell, copper ions become solid copper. So this would be the line notation for the galvanic cells seen here. Some people refer to this as an ion sandwich, because you end up with a sandwich of ions, as oxidation will always produce some ion and reduction will always reduce some ion. So a couple mnemonic devices help you remember what we went over today. Oxidation occurs at the anode, anox. Reduction occurs at the cathode, red cat. Cathode has a T in it there, so that can help you remember that the cathode is the positive side, anodes have to be negative, and that electrons flow from the anode to the cathode. And while this acronym, fat cat, is there to help you remember this, I also use this to remember that fat cats always get fatter, and so the cathode will usually increase in mass if there's a solid state electrode. So in exercise 12, you're asked to label the parts of the galvanic cell produced from permanganate and ferrous solutions. Pause the video and see if you can determine what each arrow is pointing to. So here are the parts that I've labeled. In this reaction, 5 electrons are transferred. This permanganate reduction is a little more complicated than this. However, that's a fairly straightforward explanation for this level that you're at. We will talk about how you would balance that reaction later. But 5 electrons are transferred from the iron solutions to the permanganate solutions. We have inert electrodes separated by a salt bridge. For that salt bridge, you would choose a salt that's unreactive with both. And again, so I personally always just choose potassium nitrate, because group 1 metals are always soluble and nitrates are always soluble. In the anode, we have the oxidation of ferrous to ferric solutions. So I would make 1 molar ferrous and ferric solutions and put them on 1/2 cell. That would become my anode. My cathode, I would use 1 molar permanganate and manganese ions in the other 1/2 cell. And both I would use an inert electrode, so either platinum or Graphite would be acceptable. So with that being said, you can do page 15. Later in this unit, you will have to calculate the cell potential, but that is what we are going to do next time. Please don't try to do that just yet. Next time we will calculate cell potential, how much energy is actually produced by each of your batteries. I will see you then.